Say something, Menominee.
Hello? Hello?
There you go. All right. In our books, we're on 17A, and we're going to be talking about vertical asymptotes, and they ask us to answer a question about a train coming towards you. So I've got this video to watch, and it's a train coming towards you, which I suppose might not mean that much to you, but we'll watch it anyway. Now you can see the light right there. And it moves up a little bit, moves up a little bit more. Moves up a little bit more. And then all of a sudden, it just goes straight off the screen, right? So the question they ask on page 231, let's answer that. If you are standing near some train tracks watching a train approach at a constant speed, does the height of the train appear to increase at a constant rate? So the answer choices are yes and no. Is there anybody that has an answer they would like to say? Does it appear to increase at a constant rate?
I think it does.
You think it does? Why are you saying that?
Oh, well.
So it's a guess, is what you're saying?
Yeah.
Okay. Anybody else have an opinion? So remember on the video, if it increases at a constant rate, I would be going like this, right?
Yeah.
Was I going like that?
No.
No. Do you think it doesn't increase at a constant rate? My finger stayed down here for a long, long, long time, and then all of a sudden what happened? It went straight up off the screen, right?
Let's see what you did there.
Okay. Let's look at the formula that they give us for an object. Objects that are closer appear larger, while objects that are farther away appear smaller. If you talk about the 10-meter apparent height, so A stands for apparent height, of an object that is d meters away, you get the apparent height is 10 times its height divided by its distance. Now that's for an object that's 10 meters away. Obviously, you can have objects at any distance away. So we're going to talk about this formula just in relationship to D is the actual distance from the viewer, H is the actual height of the object, the distant object with a 10-meter apparent height, A, appears to be the same height with an actual height, A, that is 10 meters away. So 10 meters is about maybe from here to the door. So something that's from here to the door appears such and such a height. You can make anything in that distance appear any height. I've got another video here to watch, I think. Right here. Oops. I saw this on the at the Super Bowl one year, and I was like, "Wow, that is so cool." So they're showing full-size cars. Then you think this one's going to go between those cars, and it like is way bigger than you would expect it to be. Why? Because the apparent height was deceived by the distance we were actually from that apparent heighted object. Okay? So, let's look at the math here on this page. A Batman figure is 0.23 meters tall. A basketball player is 2 meters tall. Which appears taller? A Batman figure that is 10 meters away, or a basketball player that is 100 meters away? Set up the math for both of those using your A of D formula and see what you get for your two answers. Go. So who appears taller, Batman or the basketball player? Did you do the math?
The Batman figure by 0.3 meters.
So here's the math that I had. Oops. My screen froze. Here's the math that I had for this one. The Batman figure is 10 times 0.23 divided by 10 because it's 10 meters away. The basketball player is 10 times 2 divided by 100 because it's 100 meters away. So Batman appears to be how tall? And the basketball player appears to be... So who appears taller? Batman. Suppose that the basketball player, part B, stands 5 meters away and appears to be the same height as a lamppost that is 10 meters away. So I'll get you started. A of 5 and A of 10. And we know those two are equal. So do the math, compare your answer with the person sitting next to you, and give me a number that describes the height of the lamppost. Oh, remember that the basketball player is 2 meters tall. Go. Is that the math that you got? Took 10 times 2 divided by 5 because it's the apparent height is 5. It's 2 meters tall. Remember that 10 is a constant there in the numerator. 10 times 2 is 20 divided by 5 is 4. So the basketball player appears to be 4 meters tall. The lamppost is 10 meters away, so it's 10 times L. I used L for the lamppost. Divided by 10 is L. we want those two to be equal, so the lamppost must be 4 meters tall. Well, think about it this way. Here's your eye. Here's your eye, and here's the basketball player at a certain distance away, 5 meters. If you go to 10 meters away, here is the, I'll draw a lamppost like the lamp out in front of our house. Here is the lamppost. So if this is 2 meters tall, this must be 4 meters tall, right? You know that from geometry, right? Those are two similar triangles, so they have proportional parts. Questions? Okay. That's not where we want to go, though. We are going to make a composite function. It says, now a train is approaching at a constant speed where distance as a function of time is 120 minus 6t. We want to get a formula A of t. Well, we know what A of d is. A of d is 10 times the distance, 10 times the height, right? Divided by the distance. Right?
Yeah.
Okay? So wherever we see distance, we can substitute this in instead. Rewrite this formula so that you have A as a function of d of t. See if the person sitting next to you gets the same answer you get. By now, you absolutely, positively have to be able to do this on your own. Compose these two functions. Let's just make sure you can. So our base function is the outside part, 10h. Our d is the inside part. Instead of writing d here, we're going to write 120 minus 6t. Is that what you got?
Yeah.
Does it make sense? So here's our input. We are putting in time. Okay? Our output from that function is 120 minus 6 times the time. Okay? We take that, and that's the input for our second function. And our second machine takes 10 times the height divided by that distance. Well, we don't know how tall the height is, but it does say here that our train is 4.8 meters tall. So we could have substituted in it. H is a parameter here, 4.8 meters. Now, the first question is, does it make sense for a train to be 4.8 meters tall? That seems really tall to me. But have you ever been next to a train? Those puppies are huge, right? So 4.8 meters tall is not unheard of. So really what we've got here, if we wanted to simplify it totally, putting that 4.8 meters in, we would have 48 divided by 120 minus 6t. Which leads us back to what we're talking about is rational functions. What can't the time be?
Oh, 20.
20. Because if you take 120 minus 6 times 20, 120 minus 120, you get 0, and it can't be 0. Okay? Now, is that discontinuity a whole, or is it an asymptote? Check your notes from yesterday. Is it a whole, or is it an asymptote? Is it removable, or is it non-removable? Can you factor something out of the top to get that to be removable? No, it's non-removable. It's an asymptote. Is there a phone application you could use to determine whether it's removable or non-removable? Use it now. So I have it graphed here, 48 over 120 minus 6x. And what do I have? An asymptote or a whole? Everybody, okay, don't feel bad if you don't know the difference between an asymptote and a whole. I just want to know. I know the difference between an asymptote and a whole. Give me the number of fingers about how sure you are of your answer. 5, 4, 3, 2, 1. 2. Okay, how can you tell it's an asymptote rather than a whole? An asymptote is a vertical line that your function doesn't cross. So it goes up here on this side, but you don't ever get exactly to 20. You come down on this side, and you don't ever get exactly to 20. If you recall, when we were doing wholes, the line looked like a line, and the only way we saw that it was a whole was we went along the line until we got to a certain spot, and then it would say 3, comma, and what did it always say after the 3, comma?
Undefined.
Undefined. So now you see the difference between an asymptote and a whole? So in this case, is this an asymptote or is this a whole? It's an asymptote, which means it's non-removable. Okay, so, and it's at 20 seconds. Well, let's think. Why is it at 20 seconds? Here's the train. It's coming towards you. 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 And all of a sudden, it's right there. And how tall is that light? No, I can't even see the light. It's up at infinity. Okay, and then the next split second, you're dead. And then the Hark the Herald Angels will be singing. Thank you for being with us in heaven. Okay, so you get the picture here. It's at 20 seconds. So, use the formula that we just made to give us the apparent height at 9 seconds, 12 seconds, 15 seconds, and 20 seconds. Here's what I would like us to do. Let's make a table. So, add a table to our function. And instead of letting it be y2, we're going to write it as 48 divided by, I forgot what our function was, 120 minus 6x2. Okay, do you have that on your Desmos? If you don't, show me and I'll help you get it, because this is a cool way to get lots of answers at the same time. You can do it on your graphing calculator too, Maddie. I'm just not sure I know how.
Okay.
But there is you can make a table on your graphing calculator that will solve for those questions. Menominee, you guys got Desmos up and you know how to write what I just wrote?
Yeah.
Okay. All right, let's do it. Michael, I didn't see like you were for sure.
I'm
You're
good.
Okay. Bill, you good?
No.
No. Okay. Are you okay? You got the table started?
This?
No, you want a table. So, delete that X right there. Well, you can delete that one and the one above it too. There you go. Okay, now make a table. Go to. Anybody know? Oh, there it is. Over on this side. Nope, that's not it.
Should be the plus.
Plus. There you go. Hit the
Oh,
plus. Add a table. Everybody good? Okay, once you get the table made, here's why it's a cool way to do it. I'm just going to put in, on my X1 or X2s, I'm going to put in 9. I'm going to put in 12. I'm going to put in 15. And I'm going to put in, look at that. It didn't even make me put in the 18 because it said, oh, Kevin, I know what you're doing. You're counting by threes. Okay? So now I can put these values into my table in my book. 0.727, 1, 1.6, 4. How do you know that this table is not of a linear function? If it were linear, the F2s, or the F of T's or A of T's would be the same distance apart all the way down. Okay? How do you know it's inverse? A function is inverse if t times A of t is a constant. 9. So let's do t A of t. T times A of t. 9 times 0.72. Oops. Just wait. I'm doing something wrong. I have to think about that because I'm doing something wrong. I know there's something that's a constant. I'm not just sure what it is. It's not in our book. That's why it's not important. Okay. Then it says for number 5, now let's get closer and closer to 19 and see what we get. So they start out at 19.1, 19.3,
Inverse the t times a of t.
19.5, 19.7, 19.9. That's why having that in Desmos is super cool, because now we can just put into our table 19.3, 19.5, 19.7, 19.9, and we can see that our size goes from 11 to 16 to 27 to 80.
Bathrooms are down.
Right? So as we get closer and closer to 20, we see that we have an asymptote. Let's sketch the graph here. And I want to confine my graph to the first quadrant. So this is our t. This is a of t. And as we get closer to 20, our function gets to be infinity. I forgot what it was at 0. Let's see, 48 divided by 120. I don't know what that is. It's not very tall though. About a third.
It's 0.4.
1/4?
0.4.
Oh, 0.4. So at 0, it goes through 0.4. Now, when you have an asymptote, here's what you should do on your paper when you graph it, is make a vertical line and make it dashed. Why do you make it dashed? Because it's not the function. It's showing you that the function does not cross. And then if I were you, I would give it an address. I would say t equals 20. Label your axes, draw a vertical line at t equals 20. The vertical line is called an asymptote. What happens to the graph near this asymptote? An asymptote is a line the function is at infinity on one side and negative infinity on the other. Now in this case, it's on positive infinity on the left side. It will be at negative infinity on the right side. But you just can't see that right now because we aren't there. But think about it this way. Let's say the train is somehow not going to kill you. Okay? It gets closer, it gets bigger and bigger and bigger and bigger and bigger until it's as tall as you are. And after that, it's on the other side of you. It's negative, and it starts out really, really big, and then it gets smaller and smaller and smaller and smaller as it goes away. So the analogy of, or the application of the train could be understood properly, but you can't be on the railroad tracks after the train light passes you because you will be dead. Okay. Number 8. Now suppose that the train was traveling at a rate of 10 meters per second instead of 6 meters per second. Write the formula for A as a function of t. Compare your answer with the person sitting next to you. I'll give you a hint. There is indeed a rational function. Go. Numerator? Well, the train is still 4.8 meters tall, right? Still 4.8 times 10, so the numerator is 48. Now, you may not remember that it started at 120 meters away, but let's say it did. 120 minus...
6 times 10, right?
Not 6 this time. 10t, right? So now, where does the asymptote show up? Well, we found the last asymptote right here by saying the denominator is 0, or 120 equals 6t. So where is our asymptote this time? 120 equals...
I had 13 when I graphed it.
10t. Are you sure it wasn't 12?
Yeah, you're right. It's 12.
T equals 12. Now, it still starts out at 0.4 tall, but it's going up faster. Why is it going up faster? Because the train is coming toward you at a higher rate of speed, right? So it's going to reach the asymptote at t equals 12. Questions? So their question to number 9 is, how can you explain how to determine the location of an asymptote from the formula? And the asymptote is that's what she didn't say the word root, but that's correct, right? A root is a place where the function is 0. An asymptote is a root of, let's say a vertical asymptote is a root of the denominator. Good job. I'll define root here just to help you. Place where f of x equals 0. We're going to spend the next couple of lessons on cell phones and their charging. Okay. How long does it take to charge your cell phone? Is a product of a bunch of different variables, right? What are some of the things that is one of the things you need to know in order to tell me how long it takes to charge your cell phone?
Whether you have a fast charging cable or not.
Okay, how fast or how strong your charger is, that's one thing.
Big the battery.
How big the battery is the second thing, and I can think of one more that you might not think of.
If it's on or off.
Oh, I didn't think of that one. Yeah, whether it's on or off. We're going to explore that one in the next lesson.
The percentage that it's at.
Yeah, how much does it have to charge? What is its percentage that it's at? Okay, is it totally drained? It'll take longer than if it's not drained. The formula that they give us describes all those different variables, and it says the charging time The charging time is the battery capacity divided by the charging current. This is a very common equation in many fields. I'll give you an example. How long you wait in line at Quick Trip time is a function of how many people there are in line divided by how many clerks there are waiting on people. Okay, the more clerks there are, the shorter the time will be. The more people there are in line, the longer the time will be. Okay, so in this case, the time will be bigger if your battery has a bigger capacity. Time will be bigger if the charging current is smaller, or like somebody said, if you got the fast charging cable hooked up, or if you got the slow charging cable. Does anybody notice that? Like if you use your car charger, it takes longer than if you use the one in your house. Have you ever noticed that? Okay. Why is that? Because I suppose they could build a charger that would charge faster in your car, but they couldn't plug it into the cigarette lighter because that only has a certain amount of current that it's capable of giving. So they would have to put it directly into the alternator in order to, or have a wire run from the battery straight to your charger. Okay. Now, the other thing that's true is there's a problem if you get the charging current too high. Like for instance, if you hooked your battery up to the hydroelectric power plant up there in Chippewa Falls, and you hooked it up directly, your battery would charge like that. The problem is it would probably like explode. Not a good plan, right? Because it would charge way faster than it was capable of holding that charge. Here we go. The capacity of a cell phone battery is given in milliamp hours. The output current is measured in milliamps. Do you see some math that will take place with dimensional analysis when you do this? Well, these two are going to be a 1, right? And 1 times h is h, correct? So those two are going to, we say, cancel each other out. Not real comfortable with that. But that's what we got. 1900 milliamp hours. Okay. T as a function of current. Let's say T of C. Did you notice that they didn't write this in function notation? Okay? Remember at the very beginning of the course I said that time is always the independent variable? Now, that's time of day. That's not the amount of time it takes to charge your battery. We describe both of them using the same word, T, but in this case, T is going to be the vertical axis because the time that it takes to charge your battery is based on the charging current of that battery, and so we will say 1900 over C. Now, how does our book get around it? They say f of x is 1900 over x. The problem I have with that is we don't know what x is. I mean, x is a variable. But in this case, everybody agree current is the variable that we're talking about. Okay? Use your graphing calculator app. Sketch the graph from 0 to 3,000. Um, 17B. Sketch your graph from 0 to 3,000. Label the axes on your graph with the quantities they represent. So we've got a this is current C in milliamp, and this is time in hours. And it appears as though this is a vertical asymptote. And actually, it appears as though this is a horizontal asymptote. And that's true because this is an inverse function. How can you tell it's an inverse function? The variable is in the denominator. Consider output values between 0 and 12. So here's 0, 12 is right up here. Consider these output values. Okay, so we're just talking about these outputs from here to here. Consider those output values, it says. A local electronics store sells several different phone chargers rated from 700 milliamps to 21. Oops, didn't do that right. Rated from 700 milliamps to 2100 milliamps. So we're going to be talking about from 700 to 2100. (700 to 2100). What is the range of charging times? So, D goes from 700 to, I should be doing green. D goes from 700 to 2100. Range goes from, well, let's go to the graph. Range goes from 2.714 down to 0.905. Ooh, I have those in backwards order, don't I? 0.905 to 0.714. So let's make a verbal statement about this. If your charger is able to charge between 700 milliamps and 2100 milliamps, complete the statement. It will take between, do you not know, or are you just afraid to say? 0.905 hours, or 2.714 if you wanted to do it the right way. 2.714 hours and 0.9 hours for it to charge. Everybody good with that? Make sense?
Why do you have those in an ordered pair? Is that just because it's the range?
Can you say that again?
You just have those in the ordered pair because it's the range of hours?
I have them in the, that's not an ordered pair. If you notice, the notation for an ordered pair is the exact same for the notation of an interval. It's just, we are used to writing that first one as C is between 700 and 2100. And we're used to writing the other one as T is between 0.905 and 2.714. Interval note, this is inequality notation. And these two are in interval notation. So yeah, you're right, it does look like an ordered pair, but it's not an ordered pair. It's the value is between these two numbers. D stands for the domain, R stands for the range. Does that make sense to you now?
Yeah.
Okay. Let's see here. Let's see. D, the graph of f has a vertical asymptote at time equals 0. You can't have a charger that's strong enough. Vertical asymptote. I'm sorry. If you have a charger that has 0 milliamps, it will take forever to charge. Okay? How long will it take to charge your phone if you don't plug it in? That's a dumb question, Kevin. Right? It will never charge. So you can't ask a question about how long because you can't do it. It is a math that is impossible. An online store sells a cheap charger with a current below 200 milliamps. So here's that charger. Here's 200 milliamps. How long will it take to charge with that charger of 200 milliamps?
9.5 hours.
9.5 hours. Basically, you would be without your phone for 1/3 of the day. Okay? Now, even if you plugged it in when you went to sleep and got up in the morning, you wouldn't be able to play Angry Birds. You would have to give up an hour and a half of Angry Birds per day. I cannot believe I walk down the hall, everybody is on their phone. Always. I go to a restaurant, everybody is on their phone. I just don't get it. No, people don't have fun anymore. Everybody's on their phones. So, it would probably be a cheap charger, but your phone wouldn't charge. Maurice needs to charge his cell phone, but he wants to watch a video while his phone is charging. So remember when we were talking about that a few minutes ago, and somebody said, well, it depends on if your phone is on or not, right? So that person was right. I can't remember who said that. That person is right. If your phone is on, it will take longer to charge, right? It says here, the phone battery is 1600 milliamps. So it's a smaller battery than the last one. Everybody agree with that? Because the last battery was 1900 milliamps. This one is only 1600 milliamps. The current available to charge his phone is X minus 300. Because 300 milliamps of what the charger is giving out has to be used up by the video that he's watching. So his formula is, let's write it down, G of X. I don't know. I'm going to write V for video. No. I don't know. Let's do G of X. G of X is 1600 over X minus 300. So let's get started sketching that graph. The very first thing we do is this. And we write down the equation of that line. X equals, give me a number. 300. Why? Because it's the place where the denominator is 0.
Vertical asymptote.
It's a vertical asymptote. You are correct. All right? After that, we can sketch our function. So what did that vertical asymptote do? It moved our graph forward 300. Why did it go forward? Because subtracting from X, or subtracting a horizontal shift, moves the graph right. Adding a horizontal shift moves the graph left. So we went right. 300. Part A, the graph has a vertical asymptote. Where is it? It's at 300. So if Maurice used a charger with a 300 milliamp charging capacity, what would all of that charger be doing? It would be just keeping the battery where it is. How long would it take to charge the battery? It wouldn't ever charge, because as long as you're watching that video. How about if you had a 200 milliamp charger? It wouldn't even keep up with the video, right? It would be losing ground. Use a graphing calculator or app. Sketch the graph of the function from 0 to 1800. And then this time, we're not going to go 0. So we have to go from 0 to 1800. And we have to go from negative 12 to positive 12. Now, why from negative 12 to positive 12? Well, if you notice, our graph has this happening over here. In other words, if your charger is 0, you're going to run out of battery in this much time. But if your charger is like 299, it will take a long time before it runs out of battery. It won't charge. It won't be positive. This is negative down here. It won't be a positive time or recharging situation until you cross 300. Label your axes, include the vertical asymptote in your sketch. So for what values of x, I'm on part C, for what values of x is your charger going to be negative? If your charger is
Less than 300.
less than 300 milliamps. So if Maurice starts with a full battery and watches videos with a charging capacity of 280, he's going to lose how many milliamps each hour?
20.
20. How big is his battery? 1600. So he's got a lot of. He could watch videos for a long time, right? What is that, like 32 hours? But eventually, it's going to run out. When we come back from our break, we will start with number 4, because now we've got a different situation that we're going to be talking about.
Mr. Hulke, do you want me to do that retake after class?
Did you see that it's on the printer?
Is it?
Yeah, I thought there were 2 of you guys that wanted to take the test.
Those are
Did you staple them this morning?
Don't staple them because she has to run them through the scanner first anyway.
Taking it again? No, for you.
those are
Neither one of you 2 wanted to take it.
It must have been Eric.
Must have been Eric then. Okay. So anyway, yeah, if you want to do that after class.
Michael said he wants to retake it too, so if you have 2
Oh, there you go. Then Michael, why don't you take that other one, and then you both can work in the back of the room there next hour, okay?
All right.
And I'll have to tell the teacher to let you guys do that when she comes in.
We got kind of an assignment. No. So basically it's on the slides, I don't know, but you have 2 options. You can use your analysis essay to your research essay. Or you could read this, like, you get to choose from like 5 essays on the back of the book. It starts in like the 500s, I think. And you just taking different routes from that. So like one's about a lady wrote about if everybody had a wife in the world, like what it would be like to just drive that sexism or something like
Yeah.
that.
Oh,
And then another guy wrote about how went fishing in a lake, and then we go back to boating, like pollution in lakes or something. So you would take a research or an essay thing which all those things.
Didn't quite go that far. We got the heat.
Still saying
So I can definitely see the
Huh?
me too.
Why?
Did you finish that worksheet? Oh yeah, you're all over it.
It's snowing outside.
kidding me. It's still that whole day.
I got most of it done.
Like I literally said your phone.
Chapters,
I
like,
thought,
answer.
feel bad thinking about soup. You know, like I need soup. Like I need some like
But actually,
broth.
they take quite a while.
I'm not talking about that thick like chicken brown rice. You know that'd be good right now, but like I need some chicken style. To the family that like dumpling soup.
Oh, it was like the last
I kind of want that. Just send that to it. Literally what I've been thinking about. And what I will be thinking about. My mom made spaghetti last night. I love spaghetti. I just won't sell it. They kind of leave you alone. Oh, like, yeah. Garlic bread. Every weekend.
True, so,
Ready?
Funny shot.
Bigger screens, bigger phones and tablets can have bigger batteries with more capacity, but the larger screen takes more current to operate. So, you have a trade-off there, and the trade-off is this. A battery can be related to the screen size. So we've got one function that says if you have a screen size of this, that can make a battery as a function of screen size be, oops, I have that wrong. The battery as a function of the screen size is 400 times the screen size in inches minus 600. So you could carry around a phone that would be like the size of a piece of paper. Screen size diagonal would be about, I don't know, maybe 15 inches. Nah, it wouldn't be that big. 13 inches. Okay, so at 13 inches, so you could take 400 times 13 is 5,200 minus 600. So you could have like a 4,600 milliamp battery. A huge battery. Unfortunately, what happens as a battery gets bigger? Your phone gets heavier, right? Everybody agree? Your phone gets heavier. You could have a phone that is huge, but carrying it around would be like carrying around your trolling motor battery. Not a fun deal. You'd need a backpack for it, right? Now this is my phone, okay? Now you guys laugh. Back in the day, have you ever heard of a thing called a boom box? A boom box was a radio that people would carry around on their shoulder and listen to, okay? And then people said, dude, why do I want to carry this huge, heavy thing around? So then they made headphones, and it was like, oh, what a good idea, okay? Anyway, you could make a huge screen. So that's the battery size compared to the screen. Well, then it says here, a 1200 milliamp charger and it says, suppose that watching a video requires a current of 12 times the screen size squared. Now you may say, well, that doesn't really make sense, but think about it this way. If you're watching a video on a bigger screen, doesn't it make sense that the amount of battery you will use is related to how big that screen is? But there's two dimensions of that screen. There's the vertical direction and the horizontal direction. So that's why the squared comes in. Everybody agree with that? Okay, so the amount that you're going to use, the current as a function of screen size is 1200. That's how big the charger is. Subtract 12s squared. Okay. This graph has, it says, part A. This graph has two vertical asymptotes. How do we know that? You see in the denominator, that's where we're looking, right? We have an s squared, which tells you there are two roots. If it would be s cubed, there would be 3 roots, right? So there are 2 roots, and remember, the roots are the places where, so 1200 equals 12s squared. What can you do to both sides? Divide by 12 and you get 100 is s squared, which means s is, take the square root of both sides, 10. So we have a vertical asymptote at negative 10. That's a screen size of negative 10. And we have a vertical asymptote where the screen size is positive 10 inches. Now, does it make sense to have a screen size even 0? Yeah, I've got this cool cell phone. It's got no screen. We call those a flip phone, right? How fun would it be to watch a video on a flip phone? Kevin, you can't do it, right? Okay, that's what they mean when they say the denominator can't be 0. Okay. What are we on here? Do they both correspond to a reasonable screen size for a phone or tablet? Everybody agree? This one over here is useless. B, find all the values of s for which h of s is 0. New concept. I don't know, why does this thing not turn pages? There we go. New concept. Zeros of the numerator are zeros of the function. Find all the values of s for which h of s is 0. Also, h of s is 400 s minus 600 over 1200 minus 12s squared. The only thing we have to pay attention to is the numerator. And what are we going to write? 400 s equals 600. So s is 1.5. Okay, so we take our graph that we started. We had an asymptote at negative 10. We have an asymptote at positive 10. And now it says we've got a 0 at 1.5. I better write S equals 10. 1.5 comma 0. What does that mean? Well, it means if you have a screen size of 1.5 inches, your battery will not exist. C, use a graphing calculator or app. The thing let's see, and then make sure you go so that S goes from screens graph. S goes from 0 to 16. And if S goes from 0 to 16, now I want to show you that I stopped my graph at 0 because we aren't talking about to the left of 0, but it goes through 1.50. So in other words, if you had a screen size of anywhere between 0 and 1.5 inches, you would have a negative sized battery. Your screen is too small to put a battery into that phone. If you had a screen size of exactly 10 inches, if you had a screen size of exactly 10 inches, your, what's H of S? The time to charge will be infinity because the phone is using up more power than the charger can give off, or than the battery can absorb. Could have you graphed first and then answered these two questions? Sure. Where are the vertical asymptotes? Well, for one thing, you might have to zoom out a bit to see that the other vertical asymptote is at negative 10. Could have you found the zeros? Sure. Once you click on the graph, it automatically gives you the 0 values. Okay? So don't be intimidated by being given a function and then asked to answer questions. Graph it if you're not sure. Questions?
So can the screen never be 10 for this size?
No, the screen, you can make a 10-inch screen. It's just the amount of time that the battery is capable of charging that will be an infinite amount.
Okay.
C, or D, I'm sorry. What interval of screen size would allow the phone to recharge in a reasonable amount of time? Somewhere between 1.5 inches and 10 inches, it will be a reasonable amount of time, right? I mean, you could wait, say, an hour. Well, this is 2 hours. If you wait 2 hours, you could have a 5.5-inch screen. I don't know, maybe 6 hours, you could have an 8-inch screen. But if you had a 10-inch screen, I don't think you want to wait around for it to charge. I mean, it would take forever to charge at that rate. Okay. For what interval of screen size would it lose charge noticeably while you're charging? Well, it would lose charge anywhere from 10 to about, 15 hours. Or I'm sorry, 10 to about 15 inches. Page 239. Can you make your shadow move faster than you move? Draw a diagram. I'm going to have to shoot this video because we have a really cool street light at our house now. It's one of those newfangled LED ones. Does anybody have one of those at their house?
Yeah, just changed our.
Oh, they are awesome, right? They give you a really, really, really crisp shadow. Okay? So as you walk away from the light, so let's say the light is back there. As you walk away, do you agree that your shadow is growing longer the farther you walk, right? Well, the shadow, if it's growing longer as you're walking, the shadow is moving faster than you're moving, right? So let's draw a diagram to show that. Okay, so here's the light. If you are here, your shadow is down here, in which case your shadow is going slower than you are, correct? But if you're out here, your shadow is this long, right? So if your shadow is shorter than you, it's going slower. If your shadow is longer than you, it's going faster than you're moving. Does that make sense? Right? You get the picture? Page 239. My first question to you is, what do you have for a formula here in your books? H of t equals. What does your book say?
We have A of t equals.
Keep talking. Is it 48t minus 16t squared?
Yeah.
Yeah.
You have A of t?
Oh, I'm looking at that. I was looking at that first.
You have this one down here as A of t.
Yeah.
Does this one up here say H of t?
Yes.
Okay. A of t is always the average rate of change formula. It is also called the difference quotient. How am I showing a difference quotient? Well, I'm showing you the quotient part is the divide by sign, right? Because a quotient is a division. Difference is, they say, h of 1. Oops, I did that wrong. H of 1 minus h of t divided by 1 minus t. So we're only talking about the domain. We're only going to graph from 0 to 1. Let's find out what is h of 1. Well, it says h of any number is 48 times that number minus 16 times that number squared. So if we substitute 1 in here and 1 in here, what do we get for an answer?
$32.
Everybody agree with that? 48 times 1 is 48. 16 times 1 times 1 is 16. 48 minus 16 is 32. Subtract h of t, or minus 48t minus 16t squared, divided by 1 minus t. Let's rearrange this function so that it looks right. Minus negative 16 is 16, correct? 16t squared minus 48t plus 32 divided by 1 minus t. One more thing we should do, and that is change everything's sign so that this denominator is written correctly. T minus 1. So when we do, we get how can it be so painful, Kevin? There. So we get a of t is negative 16t squared. Plus 48t minus 32 over t minus 1. Why is that important? Let's graph that function. Instead of following their directions, let's just graph it.
The camera.
Now, why did I graph it this time rather than go through this part here? I drew the graph on purpose because I could look at this formula and I could say this numerator has a factor of t minus 1. But it's possible you wouldn't see that. If I factor a negative 16 out of everything, then this becomes t squared, this becomes negative 3t, and this becomes plus 2. And the two factors of that are t minus 1 and t minus 2. Now, when I factor this, this is a removable removable discontinuity. Why is it removable? Removable just means common factors. So since it's a removable discontinuity, there will be a hole at t equals 1. So we can look at our graph, go over to t equals 1, click on it, and it will say 1, comma, undefined. If we just looked at the line without that, it would appear as though it's a solid line. So when we sketch the graph and we see this, we're tempted to draw the whole thing. When you see that line, and you see that this is a rational function. Everybody agree it's a rational function because there's a variable in the denominator. But the graph of it looks like a line, correct? It must have a removable discontinuity in it. That's the only reason that you could end up with a linear function. So you have to find where that is. Now you could go through every value along here until you find it, but the other way to do it is to just say 1 minus t, t must be 1. 1 minus what is 0? 1. The other thing that you'll notice is our graph goes through, so this is 1, comma, undefined. And this is 2, comma, 0. Why is it 2, comma, 0? Because it's the other factor of the top. Why didn't you have an asymptote here at positive 1? Because the asymptote you would have had was canceled by the 0 you would have had, and so those two things cancel each other out. We're going to work in calculus that is one of the indeterminate forms, where you have like 0 over 0. What happens when you have 0 over 0? Well, some people say the answer is 0. Other people say the answer is 1. Other people say the answer is undefined. And all three of those are possible. You need to figure out which one of those works with the case that you're talking about. So this is an indeterminate form where the t minus 1 on the top cancels the t minus 1 on the bottom. Page 240. Number 3, does the graph of A have any vertical asymptotes? Number 3. Oh, did I skip a page? Are we okay? We're on the right page, right? Does it have any vertical asymptotes? No. The most common wrong answer is a vertical asymptote at 1. But remember, you have to find the zeros of the numerator and the zeros of the denominator before you can say it has one. Use a graphing calculator or app to check your answer. Use the formula to complete the following table. As t gets closer to 1, how do the values of a of t change? Okay, so they say t is 0.9. So I'm going to put in 0.9. And put the graph in. And if it's at 0.9, what is the average rate of change? At 0.9. What does it say? 17.6, right? Then it says t goes to 0.99. A of t goes to 16.16. T goes to 0.999. $16.016. And then 4 nines. $16.002. Then I'm going to add one more on my table. So put one more on your table right below that. Right, 1.0001. So let's just go to just the other side of that as we get closer and closer and closer to it. So I'm going to write 1.0001. And if you notice when I do, it's 15.998. Okay. So while it says at 1, the value is undefined. As you get closer and closer and closer to 1, what answer does your function get closer and closer to? 16. So you can tell what the address of a hole would have been by just figuring out, well, as you get closer and closer to that, what happens. So what it's saying is, as you get closer to 1 second, according to this formula, while it appears as though there is no value, you get closer and closer to a certain value. If you go back and look at that graph that we drew here of the person's shadow, at 16 meters, the person's shadow would have been the exact same height as the person. So is it moving faster or slower? It's not moving faster or slower. It's moving at the same speed. Got it? All right. Page 240. Now suppose there is a very bright light. Is your light pole 64 feet tall? Does your diagram match this one? 64 feet, 100 feet, H of t, D of t?
Yes.
Okay. They give us the formula that says distance as a function of time. In other words, the distance that the shadow is passing is 100 times 3t minus t squared over t squared minus 3t plus 2. Page 241, up at the top, it says, give the equation of all the vertical asymptotes of the graph. In order to do that, we had a number of different ways that we could do that. Choose the one that you like best and find the equation of those vertical asymptotes. Go. And while you do that, I'm going to take attendance. Nick, Michael,
Yep.
Marlena, Gavin, Janae, Felicia, Nicole, Eric, Phil, Grant,
Here.
Connor, Laura, Madeline, Jessica, Lauren, Jake, and Sam. Okay. You know, I'm kind of torn as to which one I like better. Since I already have it entered in my Desmos, I'm going to just graph it. I got to make sure I graph the right one here. Which one is it? 100 minus this one right here, right? Now, the other way that you could do it is on your paper, you could factor the numerator and the denominator, and the numerator factors into 100 times t. If I take a t out of both of these, I'll have 3 minus t. In the denominator, I can factor the denominator, and I get t minus 1, t minus 2. So, since I already looked at that graph and I saw what the graph was, I'm just going to draw my asymptotes here at 1 and at 2. And I'm going to write t equals 1, t equals 2. And then I'm going to put in my 0 for the numerator at 3. So those are 3 parts of the graph that I can get automatically. So it goes through 3. Oops, I missed the other one. It goes through 0 also. T equals 3, t equals 0. So the only thing that I don't know is I don't know that it goes up like this on this side of the asymptote, and it goes down like this on this side of the asymptote. Those are the 2 parts I don't know. So in other words, as I get closer and closer to 1 second, my shadow is moving faster and faster until it goes to an infinite speed. As I get farther and farther away from 2 seconds, my shadow keeps on slowing down until it is going backwards. Well, what's happening is, remember, here's the light on the light pole, and here is your projectile. It's going up into the air, and then it's coming back down. Well, once it gets to this spot right here, everybody agree, the shadow is going to be at infinity. So as it's going up, the shadow goes from this to this to this until it gets to 1 second. Then the projectile starts coming back down, and it reaches this point, then this point, then this point, then this point. So on the way up, the shadow was going longer, and on the way back, the shadow is getting shorter. So they show that on our graph like this. There is no shadow at 3 seconds. There is no shadow I'm sorry, the shadow is moving at a 0 velocity at 0 seconds and 0 velocity at 3 seconds. Page 241. Use the formula to complete the following table as shown. So let's make a table where we have 100 times x2 times 3 minus x1 divided by x1 minus 2 times x1 minus 1. And if you notice, I get those values when I plug it in. So at 0.9 seconds, my shadow is 1,700 meters long. At 0.99 seconds, my shadow is 19,000 meters long. At 0.999 seconds, my shadow is 199,000 meters long. 0.9999, my shadow is 2 million meters long. Got it? How is this table different from the table on page 240? That's what we want to notice for our notes. Oops. How are these two tables different? Here's the difference. As you went down on page 240, they got closer and closer to 16. As you go down here, they get bigger and bigger and bigger until they get infinite. This is an asymptote table. This is a whole table. So you might want to write above them asymptote and whole so that you can see the difference. So, for our functions, write the formulas for A of t and d of t. Well, we already did d of t. D as a function of t was 300 times t minus 3 over t minus 2 t minus 1. A of t we wrote as, where was that? A of t was 16 t squared. Actually, it was negative 16 t squared plus 48 t minus 32 over t minus 1. Actually, let's write it in the factored form. Negative 16 times t minus 1 times t minus 2 over t minus 1. So those are our two functions, A, D. So what are the zeros of the numerator? Well, here the zeros are at 0 and 3. Here the zeros are at 1 and 2. What are the zeros of the denominator?
2 and 1.
Here they are 2 and 1. And the numerator, just 1. Vertical asymptote. I'm going to tell you why there is no vertical asymptote. There is no asymptote because the 0 on the numerator matches the 0 of the denominator. Where are the vertical asymptotes here? At 2 and 1. Why 2 and 1? Because the vertical asymptotes have the same address as the zeros of the denominator. Page 17D. More on vertical asymptotes. Suppose you have a pair of strong magnets that attract each other. What happens as you move the magnets closer and closer together? Eventually, as you move them closer and closer together, their attractive force is stronger than you can hold them back, and they just go like that, right? Now, if they had the same pull towards each other, you couldn't get them to touch each other. But we're talking about that you have opposite poles, so they attract each other. Opposite poles attracting each other. Here's the example that they give. Many quantities in physics, such as gravitational attraction between planets or intensity of light transmitted from the source, behave like the attraction between magnets. The closer the two objects are, the greater the magnitude of the gravitational attraction. And in fact, it's not just inverse, it's inverse squared. F of x equals 1 over x minus 5 squared. When we see this, how do you know it's an asymptote, not a hole? Because there's nothing to cancel in the numerator, right? So you have an asymptote at 5. The difference is this time we've got a squared, so let's write the word twice here. We've got a vertical asymptote at 5. Let's write the word twice. And we're going to see why that's important in this lesson. So here's what they're saying. If two objects are placed on a number line, one at point 5 and the other at point x, as you get them closer and closer together, they attract each other, right? If this one is at 5x, as they get closer and closer together, they eventually attract each other, right? Do you like those sound effects? I worked on that all night long. Didn't even go to bed just to look at it. Without graphing, can you tell where the vertical asymptotes will be? So 5, 4, 3, 2, 1. When I looked at that, I knew where the vertical asymptote was. We've got a 4. We've got a 3. We've got a 3. 5, 4. So you looked at that equation. F of x equals 1 over x minus 5 squared. 3. Okay. Eric, I didn't see your fingers. Okay? Okay. Hey, here's a question. How many of you, when you looked at it, knew it was a rational function?
No.
What does a rational function mean? A variable is in the denominator. Here we go. Without graphing, how do you know f of x is always positive? Looking at that, how can you say, oh, f of x has to be positive? Very good. When you square a number, it's always positive, right? And 1 is positive. What's a positive number divided by a positive number? It's always going to be a positive number. So on our graph, we automatically know our answer is going to be up here someplace. It can't be below. Now I want you to see why we wrote that x equals 5 twice. Do you recall what we said before about the asymptote? As you get closer to the asymptote on this side, you're going to go up or down. As you get closer to the asymptote on this side, you're going to go the other direction, right? What do you think that twice business has to do with it? Since it's twice, they're either both going to be up, or as you get closer, they're going to both be down. Now, in the connection with these magnets, how do you do the magnets so that instead of always being positive, it's always negative? Turn the one magnet around the other way, right? Now as you get them closer together, they're going to repel each other. The force is going to get negative rather than positive. Page 244. We investigated 1 over x minus 1. When we did, or x minus 5. When we did, as we got closer to 5, it went up on this side, it went down on this side. In this case, as we get closer, it's going to go up on both sides. We'll start with page 244, number 4. And then you guys can start working on that test. Open book, open notes, can't phone a friend. And then have, what's her name? In the office, just fax them to me and send them to me. Thank you. Rose, that's her name. Rose Hansen.
Is there another class after this? No. I didn't even need to move that.
Okay, here's the situation. Today, I'm going to be teaching in room 230 at noon. Does that work for you? Tomorrow, I'm also going to be teaching in there. But then I've got a class. So, 2:30. Yep, room 230, 1 o'clock, or 12 o'clock. And I will print off a test now so that I have one when you show up.
And then how many tests are there?
4. And we've already had 1. So we need, we've already had 2, so we have 2 more left.
Okay, so is there any chance, like, because I've been getting like 2, so like, is there a chance I could retake the first one at any point again, or is it after like the second test?
Did you take the first test twice already?
I think I did, but I gotta see.
The second time? I'll have to see if I can find another version of test 1. I don't know that I've got another version, so that's...
Well, I can tell you I don't remember. But yeah, I'm just trying to get that date.
Yeah, I'm fine with that. I just don't remember if I've got another version. So, like you said, we might have to take this one. Take one of the 2 versions that you've already taken.
Okay.
Okay?
All right, thank you.
Yep.